In this final video for section 3.2, we're going to look at integrating powers and products and powers of tangent and secant. So to begin with, these are some basic integration formulas that if you don't remember them, you may want to keep them in the back of your mind. Particularly the bottom two that you'll use a few times. The antiderivative of tangent is the log of secant, and the antiderivative or integral of secant is the log of secant plus tangent absolute value. So once again, we have this box with these very complicated looking rules or strategy in it. So I'm going to go through about 5 problems and try to summarize what is basically in those little boxes. So in these problems, we have mixtures of tangents and secants raised to some power. So one of the first things we want to look for is we want to look to see if secant is raised to an even power. The way that I kind of break it down in my mind is I'm looking for either secant to an even power or tangent to an odd power. Those are 2 different basic strategies: secant to an even power and tangent to an odd power. In this particular case, we have secant to an even power. So the strategy is we're going to break secant to the 4th into secant squared times secant squared. Then we're going to use secant squared x is equal to tangent squared x plus 1. This is another one of the Pythagorean identities. And we will substitute that in here for one of the secant squareds. So secant squared, I substituted it in for the secant squared in the middle. For that one. And then multiplying these through to get this, we have tangent to the 8th plus the tangent to the 6th, all times secant squared. So now I'm going to multiply everything through there by secant squared and put it in its own integral, just like I did with the sines and cosines. And so we get tangent to the 8th times secant squared. We get tangent to the 6th times secant squared in their own integral. Now, why do we want to do this? It's easier to see it once we get it to this point. We're going to use U-Substitution, okay? In this case, U is equal to the tangent of x. And what is the derivative of that? The derivative is secant squared x dx. Or dx is equal to du over secant squared x. Now, I didn't show the U-substitution part, but when you substitute in, take out the dx's, and you put in this, the secant squareds are going to cancel out. So we've got a beautiful little U-substitution problem here. Same thing over here. We take out dx, we put in what dx is equal to, and the secant squareds will cancel out, and so we basically have u to some power. Well, in the first one here, this is u to the 8th power, or tangent to the 8th power, so it's going to be tangent to the 9th times 1/9. And the second one is going to be tangent to the 7th times 1 over 7. So we're getting it to the point here where we can use U-substitution. And again, I didn't actually show the U-substitution. I'm just explaining that it is U-substitution. So we're looking for a power of tangent being multiplied by a secant squared. And so that's why we're looking to see if we have an even power of secant squareds, because we want to leave one secant squared to be my part of my dx. And then the other even power of secants we can convert into tangents using this formula. The next one, we have a tangent to the odd power, but there's no secants involved with it. So what do we do here? Well, let's go back to our Pythagorean identity. Tangent squared is equal to secant squared minus 1. Now, in the previous problem, we had secant squared is tangent squared plus 1. So we're just algebraically rearranging these differently. And so we break up tangent cubed into tangent times tangent squared. And so we then substitute this in, right there, substitute that in for tangent squared. Multiplying through, we end up with this. And then breaking up to their own integrals, we have two different problems. In the first one here, it's just like we did in the last problem. It's a U-substitution, where u is equal to the tangent of x, and du is equal to secant squared x dx, or dx is equal to du divided by secant squared x. So the secant squared x cancel out, and you simply have a u to the n problem. So tangent is to the first power, raised to the second power, times 1 over 2. And in the second one, we have the integral of tangent, which is one of those integrals right at the beginning of this video. So you should know the integral of tangent is the log of secant of x. And that's that. Next one up, we have secant to an odd power. So in the first problem, I said, we're looking for secant to an even power. What do we do if we have secant cubed? Well, the strategy for this is a little bit more complicated. If we break this into secant squared times secant, then we have to use integration by parts. Integration by parts. Believe it or not, that's what we have to do. So if we let u be equal to secant, then the derivative of that is secant tangent. If we let dv be equal to secant squared, the antiderivative of that is tangent, because the derivative of tangent is secant squared, the antiderivative of secant squared is tangent. That's the way I usually remember those. And so plugging those into your integration by parts, we have secant tangent right here, minus the integral of tangent, secant tangent, which is tangent squared secant. Okay, so now we need to integrate this. So how do we integrate that? So we're going to use our Pythagorean identity again. Take out the tangent squared, put in secant squared x minus 1. Multiply that through by secant. We get secant cubed x minus secant of x. Breaking them into their own integrals, we end up with this. And then the integral of secant is the log of secant tangent. And we have a secant tangent. And then what do we do with this? That's the tricky part. Well, notice we have the integral of secant cubed. Well, that's what we started with. We started with that. So basically, I wrote it a little bit better on the next line. I wrote both sides of the equation. So we started off with the integral of secant cubed x. And so what we're going to do is we're going to take this and subtract it over to the other side of the equation. Actually, this is a minus. So we're adding it to the other side. So we end up with 2 secant cubes. I think I got my signs wrong there. Yeah, I switched these two terms around, but I didn't switch the signs, so I don't want to get anybody confused. It looks like this term came over here, so that should be a plus. That should be a minus. All right, so when we take this minus this term and we add it to the other side, we end up with 2 times the integral of secant cubed x dx is equal to this stuff right here. It becomes this stuff right here. And then just to get rid of the 2 right here, we multiply everything, multiply both sides of the equation by 1/2, and that's where all these 1/2s come from. Voila. So there's another new strategy. And you'll see that from time to time, where on the right-hand side, you end up with minus the same thing that's over on the left-hand side. And so you just add it over on the other side to get two of them and go from there. So kind of go through this one a couple of times. If it doesn't make much sense to you, let me know, and we can go over it again. Okay, here's one where tangent is odd. So way back at the beginning, I said, I like to look to see if secant is even. And when secant is even, we're ending up trying to do a U-substitution with a tangent of some power, a tangent to some power n times a secant squared x. So we're using U as tangent. However, if we have a situation where tangent is odd, we have another strategy. So let's break tangent to the fifth into tangent times tangent squared times tangent squared. Tangent squared is secant squared x minus 1. Substitute those in for the tangent squareds. Multiply them together to get secant to the fourth x minus 2 secant squared x plus 1. And times this stuff right here. And I just put the tangent out at the back end. Now what I'm going to do is I'm going to multiply the secant cubed through all of this to get this. Okay, so secant to the fourth times secant cubed is secant to the seventh. Then we get a secant to the fifth. And then we're getting 1 times secant cubed is a secant cubed. All times tangent of x. So now what I'm going to do is I'm going to multiply everything through by the tangent and put them in their own integrals. So I have this, I have this, and I have this. One more step. Factor out a secant from each of the secants. So secant to the seventh, I can factor out a secant, and we would end up with a secant to the sixth times a secant times tangent. Secant to the fifth, right here, factor out a secant, we end up with secant to the fourth times secant times tangent. And secant cubed, we end up with a secant squared times secant times tangent. Now, some people like to factor out that secant, closer to the beginning of the problem. In other words, you could have done it up here. Nothing wrong with doing that. Maybe it's a little bit simpler. Way back up here, factor out a secant, and you would end up with a secant tangent here, and you can just kind of set that aside. Because what we're going to do now is we have this secant tangent in each problem. And so the derivative of secant is secant tangent. So what we have are powers of secant. We can now use U-substitution. The U-substitution that we're using is with U is equal to the secant of x, and the derivative of secant x is secant x tangent x, which is what we have attached to each one of these. So when the power of tangent is odd, we're shooting to do a U-substitution like this, a power of U, with the derivative of U being secant tangent. All right, from here, it's just, I didn't actually show the U-substitution, but you can kind of do it in your head. Secant to the sixth becomes secant to the seventh times 1/7. Secant to the fourth becomes secant to the fifth times 1/5 times 2 is 2/5. Secant squared becomes secant cubed times 1/3. And there we have it. Again, do these problems a few times. If you take the time, go over these problems in my notes on your own, try to do the work, try to reason your way through these problems, mix them up, and then go back and watch these videos. You'll get it, I have no doubt. These will be a piece of cake. Last one. Here's another one. We have tangent is odd. So with the tangent is odd, again, we're shooting to get a U-substitution where we have U is some power of secant, and so du is going to be secant x tangent of x. That's what we're shooting for. So when tangent is odd, we start by factoring out a tangent. We're going to use our identity again. So we break tangent cubed into tangent squared tangent. Bring that tangent out to the end. Substitute in this here for tangent squared. And then we're going to multiply this times secant to the 7th to get this. Now, at this point, some people would factor out a secant. Okay, you could factor secant out of both of these and attach it with this tangent. You can do it now, you can do it later, whatever you like to do. Somewhere along the line, you've got to factor out a secant. So I did not do it that way. Oops. So I'll continue doing it the way I did do it. So I multiplied these through, put them in their own integral, and then multiply secant to 7 times tangent. Then I factored out the secant, okay? So secant to the 9th became secant to the 8th times secant tangent. Secant to the 7th became secant to the 6th times a secant tangent. And now we can use our U-substitution. So secant to the 8th becomes secant to the 9th times 1 over 9. Secant to the 6th becomes secant to the 7th times 1 over 7. Boom. So that is it for this section. There's a lot of problems in this section. Please take your time. Do these problems multiple times. Try doing the problems here in my notes along with trying to do the homework problems. And spend some time with this. This is one of those sections that you've got to spend some time with, and eventually it will all fall into place and make some sense. I guarantee you it will. All right, have a good day.